Good morning, good afternoon, everyone. I'd like to start with a story from about 15 years ago. I was at a Search for Signs of Life Beyond Earth symposium at the Vatican, and it was all very civilized because only one person could talk at one time. There were like these microphones and you pressed a button. So I was giving my talk, and towards the end, I just said, for biosignatures, it'll be very hard to be sure we have found a sign of life because there's so much context to the environment and so many unknowns on exoplanets that may be providing false positives. So sitting right across from me in a room full of about 30 people was Jill Tarter. And she pressed her button, thus cutting me off and giving her the floor. And she just said, "We'll know." And she meant that for technosignatures. I think she meant that for like radio communication, we would be sure there was a sign of life, there was life. So today I'm going to be talking about something kind of in between biosignatures and like an ultimately incredibly robust radio mass communication from a technical civilization, and that is about technosignature gases. I did pick one thing to draw on, and it will take me my introduction to give you the background, which will also help motivate why we landed on NF3 and SF6. And I should also add, I had at the beginning of my talk a reference. This work is based on a single paper with my co-authors listed here. So I've been working on exoplanets for probably 3 decades. And about 20 years ago, I started at MIT, and I needed to have some ambitious goal. I wanted to have long-term investments. So I came up with one idea to try to come up with every kind of molecule that could be in gas form at a habitable planet's conditions, like temperature and pressure, so that we could have a list of all volatiles, all gases, in the hopes that we could be ready to identify a gas that was way out of equilibrium with its environment and thus could be a potential biosignature gas. So what this involved was quite a lot of work. I mean, it has taken on and off for a couple of decades, but we just started out with combinatorics, putting together the big 6, CNHOPS, and asking ourselves, this was about 6,000 molecules, by the way. Then we had to figure out what structures they could be, because different arrangement of atoms make different molecules. We got to like nearly 30,000 molecules. Then came the hard work of figuring out which of these molecules are stable, and which actually exists if it's known at all. But long story short, we ended up with a couple of databases, one with all the gases, and all the gases life produces, by the way, which are about 14,000 gases. And we also ended up with a molecule of basically every compound, known compound to be produced by any kind of life on Earth that has been reported in the literature, and that's about 200,000 compounds. So I'm just giving you background still, because it's still about biosignature gases and what we did with this giant database. And basically, everyone is familiar with oxygen as a biosignature gas. I mean, it's not a biosignature gas conference, so I'm going to go through this a little quickly. But we have oxygen, we have simple gases that are produced by simple single-celled microbes or other simple life that is exploiting chemical energy gradients. We have more complex molecules like dimethyl sulfide has been in the news, most for unspecified reasons like hormones or signaling. In fact, life produces thousands of molecules, mostly in tiny quantities. So we went through this giant exercise of going through chemical space, like that space of kind of all possible molecules, but here limited to what life on Earth produces. And we basically came up with these databases and a kind of baby initial steps to getting handle on gases that might be a sign of life in the context with their environment. So I hope you're all with me, but whether or not any of that landed, why did I give you all this giant background? Because to tell you, we have a unique database and we found something even more interesting. And that is thanks to my brilliant partner on this, Janusz Petkowski. In kind of staring at this database and curating it and finding all the literature examples, he realized that some molecules, or we call them chemical motifs, parts of molecules, are literally rarely or never produced by life. And now we have like a numerical tabulation of all of those. So I'm working my way to tell you about the focus of this talk, which is NF3 and SF6. But before that, I just have one example I wanted to share with you to further give you a bit of the meat behind this series of databases. So here is part of our periodic table. And the colors represent how common an atom is in molecules that life produces or uses. We call those natural products. So you can see on the top green, carbon. Obviously, you already know that. It's very common. Most molecules made by life pretty much all have carbon. You can see some opposite ones life pretty much doesn't have, some of these metals. But for this part of the talk, I just want to focus on nitrogen N and sulfur S. So you see nitrogen occurs in about 25% of all natural products. Sulfur is about 4%. So a question I pose to you is, how many molecules that life produces do you think have nitrogen and sulfur, like bonded to each other? If I were just looking at this from scratch, I'd say about 4%. I'd say, sulfur is pretty common, so maybe somewhere around 4% nitrogen-sulfur bonds. But because we have this database and we can enumerate all compounds or molecular motifs made by life, we found something astonishing, that life on Earth avoids a nitrogen-sulfur bond. This plot is showing you number of nitrogen-sulfur compounds, and on the bottom it's just different states of sulfur. But you can see industry is making thousands and thousands of molecules. And the same sulfur state, tiny amounts have nitrogen-sulfur bonds. So although nitrogen-sulfur chemistry is a pillar of modern industry, with lots of compounds and a wide variety of structural types, nitrogen-sulfur bond-containing compounds are rarely produced by life. There's literally only 100 molecules known. That's 0.05% of all products. And these that are produced, they're produced like as toxins towards other life forms. So it's not part of this talk. I've given you reference, but there is a reason, and we discovered, and we did some simple laboratory experiments to substantiate this hypothesis that nitrogen-hydrogen bonds are incompatible with life's very, very common sulfur-hydrogen bond. It's fair to say that the sulfur-hydrogen bond, called thiols, in the form of our essential amino acid cysteine, it's literally in every cell of life on Earth. So this is just one introductory example for our database, how we showed that life's avoiding a certain compound because it's incompatible with our life's core biochemistry. But you could imagine that life elsewhere picked NH bonds and not SH bonds, and therefore had like a different kind of biochemistry. Nonetheless, I want to say that this database, what it allows us to do was to go through chemical space and find what life avoids. And we have like a research program going on to find out, why is life avoiding that? And the relevant point out of all of this for us today is, are there any universal rules to which chemistry, life on Earth, avoids that may be universal in our universe? And if so, could these rules lead us to robust technosignatures? So that's the question you should be carrying in your mind as I go on to the next part of my talk. And this is about NF3 and SF6. Are these robust? Could they be like universally avoided by life? So FYI, from this database, life on Earth has never, like as far as we know, made a nitrogen fluorine or a sulfur fluorine bond in a one of life's products or uses. So that right there is a motivation. SF6, sulfur hexafluoride, it's completely chemically inert. It's essentially invisible to biochemistry. Sometimes I give part of this talk to like a physics audience, and the physicists will have heard of it if they do experiment, some people in some areas of experiment, because they use it as like a filler inert gas. Some of it leaks, by the way, out to our atmosphere. NF3, nitrogen tetrafluoride itself, is not quite inert, but almost. It's mildly reactive. And here's a picture of them on the right. And I have a little note to you at the bottom. This has definitely been mentioned before my paper, and it also came after. I think it's definitely a gas of interest for more study. So what I'm going to go do now is go through 5 reasons why these are great technosignature gases. And the first reason has to do with fluorine. And in our database, we're able to quantify why fluorine, how common, or rather how extremely rare fluorine is in life's molecules. So out of like thousands and thousands of molecules made by life on Earth, the halogens or the halogens like chlorine, bromine, they're quite common actually, but fluorine is basically avoided. The compounds in our database, there's like literally only 34 out of 200,000, and only 2 of these are gases. To substantiate this on the right, for comparison, here are average concentrations by mass for chondrites. And you can see you're supposed to take like these ratios, like fluorine 92 plus or minus 20 part per million, chlorine 717, etc., and compare it with the ratio in this little table. And you'll see if you do that, that life is not using fluorine in the proportion that it exists in nature. So life largely excludes fluorine from its repertoire. In the same one, life produces very few fully halogenated volatiles. In this plot on the left here, it's showing you a bunch of molecules. What's not shown is like the carbon in the center of each of these molecules. But if you look on the far left, not made by life, you could imagine having a CH4 where each H is substituted by chlorine, bromine, iodine, or what have you. These ones are not made by life. Life makes very few molecules that have every hydrogen substituted by a bromine, chlorine, or iodine, and no fully fluorinated molecules exist in nature. Moving on to the second reason, life on Earth, although it does produce like a minuscule number of compounds with fluorine, all of those are bonded to carbon. So life on Earth produces 0 fluorinated carbons where the fluorine atom is not directly bonded to carbon. Here on the left is a table showing you a bunch of different molecules that are fully fluorinated with non-carbon atoms. You can just read this list if you want, and I've highlighted the molecules we're talking about today. And you could go through this list and ask, are any other, aside from NF3 and SF6, suitable technosignature gases? And you'll see that largely the answer is no. Many of them are highly reactive. Silicon tetrafluoride is made by Earth's volcanoes. This other one, PF3, breaks down in water. Okay, so the third reason, and one of the main ones, is that these technosignature gases, they have no or nearly no false positives. And in this figure, this comes from Earth's studies, industrial pollutants rise over time. And here you can see fractional gas abundance in part per trillion. And I'm pointing out SF6 in pink and NF3 in yellow. And these other ones are just other molecules, like industrial pollutants. And you can see that like since pre-industrial time, actually this plot doesn't go as far back to pre-industrial times, but you can see the recent incredible rise of these gases. It's only due to industrial use here on Earth. This plot here comes from a report on climate change, and in this report, there's more information about how these molecules are, they punch well above their weight, so to speak, because their spectral features occur in a region where the dominant background gases of Earth's atmosphere are basically absent. So they end up being incredibly powerful greenhouse gases despite such tiny amounts. They occupy a region of the spectrum where there are no major gases absorbing. So I just wanted to unpack what no known sources means, actually, because it turns out that nature only has the same molecule. Well, nature surprises, let's just say. So in terms of this plot is showing you the standard free energy of reaction versus temperature. And if some of you can dig back into your thermodynamics, you know that negative values here mean spontaneous reaction. And the higher the number, the less likely the reaction is to occur. So in the bottom left, we're showing you some chemical reactions, and we're showing you essentially their Gibbs free energy in this plot. And what you're supposed to see here, this plot is supposed to outline for you that the formation of nitrogen NF3 and SF6 is highly thermodynamically unfavorable. That is, they don't just occur in volcanoes commonly. It's hard to make them here on Earth. And so on Earth, very trace amounts of SF6 exist in volcanic rocks in some areas, but it's very tiny, tiny amounts. When we wrote our paper, we said that NF3 has no false positives at all. But since then, we found a paper from decades ago which said that there's actually one, in my mind, obscure mineral, purple fluorite, where there's some kind of reaction that will strip off part of the mineral and release literally almost insignificant amounts of NF3. So they have little to no false positives, largely because they're incredibly thermodynamically disfavored at conditions here on Earth. Number 4, these molecules have low water solubility, and this favors their accumulation in the atmosphere. This plot is showing you a proxy for solubility where it's on a log scale, and the higher the number is, the more soluble the gas is. So you can see our gases highlighted in yellow, sulfur hexafluoride and nitrogen trifluoride, and you can see a bunch of other gases that might be familiar to you, like methane, carbon dioxide, and ammonia. And as an aside, ammonia here really stands out. It dissolves really easily in water. That actually makes ammonia a bad biosignature gas. It's hard to accumulate in the atmosphere if it's sinking into the raindrops and then raining out down to our oceans. It's also one of the reasons why nitrogen trifluoride and sulfur hexafluoride are bad, bad, bad greenhouse gases, because they accumulate in our atmosphere. They're not water soluble. But this low water solubility at the same time makes them a good technosignature gas because they can accumulate in the atmosphere. So this greenhouse gas concept relates to their unique spectral features compared to major atmospheric gases. And here, let's go over the bottom plot, which is showing you a molecular absorption cross-section as a function of wavelength. So here we have wavelength 1, 2, 3, out to 25 microns on a log scale. And you can see some of our major gases, CO2, CO in blue. And I want you to focus on this bright yellow, which is the sulfur hexafluoride. And this light blue is nitrogen trifluoride. And what you're supposed to see here, and this, by the way, this is their cross-section. There's no extra numbers added here about it. There's no gas abundance. This is just cross-section on the bottom plot. But look at these ginormous absorption features where the background gases have very little absorption, and this is what helps make them powerful greenhouse gases. But it also makes them, in large enough quantities, stand out in an atmospheric spectrum. And on the top plot, this is a simulation of transit depth as a function of wavelength to check out whether or not we can detect these gases in the near future. And the answer is no, only if you had like a giant amount of these gases. And so this transit depth is really tiny here in parts per million. You know, we're talking about like 20, 30, 40, 50 parts per million. On the bottom plots, you're seeing ones with basically, very little. Well, you're supposed to try to see these features here at 9 to 12 microns really popping out. And on the right, I've written reasons. Okay, wait, I have a jumble of thoughts here, but let me go to prospects for a moment. It would take a lot. If we imagine there's 1 part per million, of these gas in the atmosphere, which is way more than our parts per trillion here on Earth, it would literally take tens of transits or more. So it's not really feasible right now. We would need to have so much of this gas, like 10 part per million, 100 part per million. And Eddie Schwieterman has written a paper about civilizations purposely using these gases to warm their planet. So if we would like to speculate and imagine a civilization that wants to terraform and needs to warm up their planet hugely, perhaps a civilization like that needs to pump in like exceedingly what are really high amounts. 100 part per million may not seem like a lot, but in terms of when we enumerate gases in our atmosphere, almost very few gases are at 100 part per million. So the only way we could be detecting this is with a civilization like purposely wanting to warm their atmosphere, not just from leakage like we have here on Earth of these gases. So when we think about our current capabilities with today's James Webb Space Telescope, we're not thinking about Earth-Sun twins, but rather with transmission spectroscopy, we're fixated on small, low-mass planets. And furthermore, because of the tiny, tiny signals, it would really boost our case if the planets weren't like Earth with thin, high mean molecular weight atmospheres made of carbon dioxide and nitrogen, but rather hydrogen-dominated atmospheres that have more puffy atmospheres that are more easy to look at. And so I'd say for now it's not doable, but that doesn't take away from them being great technosignature gases. All right, so I only got the message of the theme when I heard Jacob giving our intro today. So I wanted to tell you about my favorite new paradigm in the search for technosignature and other gases. And this applies not only to NF3 and SF6, but also to all the chlorofluorocarbons people love to promote, and rightly so, as possible technosignatures. And because I just somehow missed the message until Jacob's intro, I didn't have time to put a slide in, so I'm going to try to explain it to you right now. And this has to do with a new type of telescope called the Solar Gravitational Lens Telescope. This telescope is futuristic, but material science for solar sails are being worked on at Caltech. And it's also this mission has been developed at JPL, a lot of work. And it has been really an ongoing mission. This mission would go to 500 times the Earth-Sun distance, 500 astronomical units, and it would use our sun as a telescope, as a gravitational lens, rather. And so the telescope concept involves the sun and this telescope at 500 AU. And what will that do for us? Well, they want to be able to put pixels all over the planet, like 1,000 by 1,000 pixels. But we've been working on high spectral resolution from that. You could literally get a spectral resolution as fine as you want, in the hundreds of thousands or millions, actually. And I do think that's what it's going to take to really evaluate all of the trace gases. And in this slide here, I had mentioned that although here at the bottom you see the cross sections really appear to be unique, it turns out that I haven't done this justice because there are so many trace gases that absorb in the 9 to 12 micron window, actually. And ultimately, to sort through those gases uniquely, we're going to need not only very high signal-to-noise resolution, but we're going to need also extremely high spectral resolution. And I've recently teamed up with Slava Turchiev, who is the main proponent behind Solar Gravitational Lens Telescope, and I have an undergrad. His name is Zane Collins, and we've been working on the case for how to separate trace gas signatures. And I really do think that's what it's going to take for us to, for once and all, find these technosignature gases. So now I'm going to move on to, why does life avoid fluorine? Is this universal, or is this just a really weird quirk of ours? And honestly, I want to just give you the simplest overview explanation, and that is the fluorine atom being extremely electronegative. It grabs onto electrons and bonds so tightly with molecules. Fluorine is like the superglue of atoms. And as you know, life really does try to use the path of least resistance energetically. So why would life want to use fluorine-containing molecules when it has to do the equivalent of removing superglue? If life can instead use molecules with hydrogen, which plays a similar role. So that's my overview explanation. In Petkowski et al. 2024, there's literally an entire paper about why life avoids F, with some legit reasons, some speculation, and more details about what life on Earth uses fluorine and why. But essentially, because of this high bonding ability, fluorine, it's mostly locked inside insoluble minerals. It is available in our ocean and ions, but on the whole, it's got low bioavailability. The high electronegativity means that life on Earth that uses these thousands of chlorine and bromine and other halogen-containing molecules, it can't use the same machinery for fluorine because of the way it is so tightly bonded. So being able to use these carbon-fluorine bonds, it's a really challenged task. And once, a couple of independent times, Earth actually has evolved these catalysts. So it's not that it can't be done. It's just that why would life bother doing it? So I'm now getting towards the end of my talk, actually, and coming back to this question that I posed to you closer to the beginning, where I was getting at, are there any universal rules for what chemicals life avoids, and could those be championed as wonderful technosignature gases? And this talk was specifically about, is life's exclusion of fluorine a universal rule, making fluorine-containing compounds robust technosignatures? And from that, I mean nitrogen trifluoride and sulfur hexafluoride, which were the molecules of this talk. But it could also be many other molecules containing fluorine. And I'm just going to pause for a moment so you can have your own thoughts to yourself about whether fluorine-containing compounds are robust technosignatures. We want to say yes. That's what my talk was about. It was about all the great reasons. But in diving into this topic, we land on a maybe, unfortunately. So we want to say yes, but we can already think of extreme cases where the answer is no. So life on Earth indeed has evolved a way to use fluorine. It is very rare, but it's a proof of concept that it could be done. Now, the kind of counterexample in our imaginations is a planet without water. That's a whole different talk about what non-water solvents life might use. But without water, there's very little hydrogen. And without hydrogen, life might have to use fluorine in place of hydrogen, not as anything functional, but as a cap. Because hydrogen and fluorine, they both have just that one valence electron opening for a single covalent bond. And so just putting a cap on the top of a molecule so it's not reactive, life elsewhere might use that actually. For the similar reasons, a planet without water or a hydrogen-depleted planet might have fluorine bound to sulfur, thus because without having hydrogen. You know how you hear about H2S? Right? So thus pumping out SF6. And indeed, there's some controversial evidence that there's SF6 on Venus, actually, from volcanoes. So I kind of now circle back to the beginning of my talk, where on the one hand, biosignature gases are fraught with false positives, and we may never be certain a biosignature gas is a sign of life. And on the other hand, a radio communication from intelligent civilization would surely be proof, robust evidence of life beyond Earth. And these technosignature gases, no matter how hard we've tried to find you a unique one that we could champion as a great sign of life, it still depends on context. And I do believe in the future we can sort through that context more easily for technosignatures than for biosignatures. But we're going to need to move to new paradigms, to way more capable telescopes of the future. So to summarize, fully fluorinated gases as exemplary technosignatures. And you notice I choose exemplary rather than perfectly robust, exemplary. Life avoids fluorine. It's nearly excluded by the chemistry of life on Earth for fundamental reasons. I gave you 5 reasons why nitrogen trifluoride and sulfur hexafluoride, NF3 and SF6, are exemplary technosignature gases. They have low water solubility, long atmospheric lifetimes, unique spectral features compared to dominant gases. Unfortunately, this is why on Earth they could be problematic greenhouse gases as they accumulate and live on in Earth's atmosphere. They do have limited false positives. NF3 has one obscure source other than industrial, while SF6, it's only produced abiotically in extremely trace amounts in some volcanoes. So our outlook is that we will add these to our list for sure, but it's still a generations-long search. And how great is it to be here among the first who get to really take this legit seriously? Thank you very much for your attention.
Thank you so much, Sara, for this very fascinating talk and interesting ideas. We have a few questions in the Q&A and about 10 minutes to talk about it. So first question from Martin Dominic. What makes a chemical system a biochemical system?
Well, we get asked that question over and over again, and oftentimes people don't have a great answer for it, including me. We want to imagine a self-replicating system. But in the case of a gas, whether it's a technosignature, well, if it's a biosignature, it needs to be pumped out by life itself.
Okay, thank you. So you mentioned some prospects with larger telescopes. So there is a comment from Mark Elowitz suggesting that LUVOIR 15 meter would be a great technosignature finder. And he suggests to use, instead of transit spectroscopy, emissive spectroscopy, or even reflective spectroscopy in the mid-infrared.
Okay, right. So regarding LUVOIR, or any big telescope, yes, it will definitely be a great stepping stone towards this. If LUVOIR has a spectral resolution of a few thousand, honestly, my personal professional opinion is that it won't be able to sort through the hopefully immense number of trace gases we're going to see in the 9 to 12 micron window. So unless the civilization has 100 part per million or some huge amount of these gases, we won't be able to uniquely discriminate them without a much, much higher spectral resolution, like the hundreds of thousands we're trying to get on ground-based telescopes for other reasons. So I don't know if LUVOIR is going to cut it. And yes, LUVOIR would be emission. I was talking about transmission spectroscopy because that's our capability today. There's no reflected light in the mid-IR. It's just thermal emission, dominated by thermal emission. So yeah, I think it would be a great stepping stone for an edge case. But if we want to get to the point where we can find what's probably more realistic, it's not going to be LUVOIR.
All right. We need something like 40 meters in space for sure. Mm-hmm. All right. Next question from David Clements. Why would a civilization want to warm its planet? Wouldn't the scale of a problem necessitating that be ultimately overwhelming, and thus deliberate warming would be at the best a short-lived and probably futile phase?
Well, I would suggest going to read the paper. I was honestly trying to be inclusive of other authors who have also mentioned this. But perhaps we could turn our attention to Mars. Perhaps those other civilizations are like us, destroying our planet, and they're going to a neighboring planet to warm it. So that question, read the paper, think about Mars or another planet.
All right, thanks. And another question from Stan Vermeijen. Have all smoking gun molecules now been considered, or are there some other places left to consider?
By the way, I need to go back and correct an answer to my question. Thank you to Nick Siegler and Ravi Kopaparu, because they answered it properly. They said LUVOIR is UV optical infrared, but it means near infrared, not the 9 to 12 micron far infrared window. But I appreciate Mark's comment because he was talking about LUVOIR class, so thinking about life or Darwin to work in the mid-infrared, they definitely don't have a very high spectral resolution. Typically, they're thinking like hundreds, not hundreds of thousands or more that we need. Okay, right. So back to the latest question. Could you please, the last one.
Have all smoking gun molecules have now been considered, or there is something else to consider?
Oh, good question. Well, in this chemical space I was trying to outline for you, what ends up happening is that, you have a set of molecules that people have looked through and combed through, but there are thousands of more molecules that we haven't researched yet, that many of them don't have spectral features. But the problem is I actually am going to bring up another plot for you. So I stop share for the moment while I'm going to bring up one last plot. The problem is that a lot of them don't have spectra, or if they do have spectra, they're very overlapping because it's like Lego pieces. Imagine if you had 20 unique Lego pieces and the more complex molecules are built from these 20 pieces. So they all have very similar pieces, and then their spectra are all very similar. So we're trying to answer that question ourselves about what are all the spectral possibilities and how to sort through them all. And so I think is the last question. So I'm going to share this very complicated plot for you. But this is showing you molecules. So this is only 600 molecules. It's not the 14,000 molecules that we have access to. These ones actually have some kind of low resolution spectra. And on the top, you can see wavelength in micron going from near infrared 2.5 out to 20. And your eye is just supposed to land where there are colors, because that's where the molecules have their fingerprints. And you can see here that's highlighted on the bottom, saturated CH. That's like your methane stretch, carbon-hydrogen stretch. And tons of molecules, so many molecules, have a really strong feature around this 3.3 micron region. But if you want to look at NF3, SF6 by these thin dashed lines at the top, they fall into this region where 9 to 12 microns, where there's not a lot that we know of. But as you can see from this plot, there's a lot going on there. There are a lot of smattering of molecules we haven't really sorted through. And so while there are a lot more molecules we could comb through, they're going to be these more complex molecules that have a lot of spectral overlap. Hence my comments on, we need to get spectra. We need to think of futuristic telescopes that could sort through all of the different trace molecules.